Hello and welcome to the second video of 1.4, the periodic table. In this video, we'll be looking at, still in the first box there, the modern periodic table showing different trends. What you need to be able to do after video is to be able to talk about valencies, the patterns in that, and what's called ionization energy and also electro negativities across periods and down the group of a periodic table. And we'll be going to slide 11 from this video. Sorry. Okay, so we'll talk about this thing called ionization energy, and this is something to do with the valency. Now, the definition of ionization energy is written there. So how much energy is required to remove one electron from valence shell? And if you have forgotten, valence shell is the outermost shell of an element, an atom. And ionization energy is the energy that's required for you to remove one electron from that shell. Now, I hope you're trying to connect that to metals and non-metals as well, because metals' tendency or the nature, so metals want to get rid of its electron from valence shell because they usually have extra electrons, and for them to be stable, they want to have octet. So getting rid of 1 or 2 or 3 electrons is so much easier. So if you are the person who is trying to get electron out of metals, you would need a lot less energy. Whereas for non-metals, because they have almost complete shell to be an octet configuration, so removing one from that is very hard because they're all tightly held by the nucleus. Yeah, adding electrons so much easier. So that's what we'll be talking about. And ionization energy is the energy required for you to remove one electron. Okay, next slide. Oops. So this slide is showing the visualization of how the ionization energy changes for each period as well as each group. Let's look at the period number 2. So lithium to neon. How does it change? Hope you can say that ionization energy is increasing from lithium to neon. Remember, the noble gases already have octet configuration. It's full of electron, its maximum number, it's the most stable number for each element of the noble gases. So they don't want to get rid of any electrons. It doesn't let you take out any electron. It's going to be very hard. That makes sense, doesn't it? Whereas on the left-hand side, you can see lithium being very low because you can take one electron off from lithium's valence shell very easily. So if you want to add note to that, talk about noble gas as well as group 1, so alkali metals. If you put that into periodic perspective, this also happens periodically. So starting from lithium to neon, you notice that the number goes higher and higher. And if you go to the next period, so starting from, sodium to argon. Yeah, sodium to argon. You would see that sodium has got the lowest ionization energy and then go up to argon. And you can see that period, that sort of pattern, the trend, keep happening periodically. Next slide is a summary. So, what do we say about reactive metals? They have high or low ionization energy. It is low ionization energy. You don't need much energy to remove. Whereas for non-metals, they would have high ionization energy. If you move across a period, what happens to the ionization energy? It increases, metal to non-metal. So ionization energy would become low to high. The reason why is written there too, because I'll put that up a bit closer. because there is a stronger positive nucleus to hold other shell electrons, outer shell electrons, sorry. This pull from positive nucleus has to be overcome to remove electron. If you have much less pull compared to the nucleus has to its outer shell electron, then you wouldn't be able to remove that electron. All right, so that was for ionization energy. Oh, there's one more, sorry. So that was for across a period. So let's look at going down a group. So moving down the group, ionization energy, what do you think? Do you remember the video, watching video for the metals exploding and the reactivity goes up? If you go from, say, lithium to cesium. Richard Hammond demonstrated that. So moving down the group, it becomes easier for the electrons to be removed, meaning lower ionization energy is needed. So in this case, you'd use the word decreases. Yeah, moving down the group, ionization energy decreases. Because the valency electrons are further away from the positive nucleus and inner shells are kind of separating the outermost shell from further away. This decreases the attractive force of the positive nucleus, and so less electrons needed to remove, sorry, less energy, that should say that, is needed to remove electron. So in another word, you can't really see that diagram there. If you go up and if you go towards left, sorry, right. If you go up and right, ionization energy increases. So that's the first thing. Now, there's another type of description that we can use, which is called the electro negativity. Electro negativity. Now, its definition is measure of the electron attracting power of an uncharged atom. So what it's saying is that each atom can attract electrons differently. Some elements can attract electrons very well. Some elements don't. Some atoms don't attract electrons so much. Now, again, I will use metals and nonmetals. Now, nonmetals, as I said before, it has nearly complete outer shell. So, for example, halogens, they want to have extra electrons, and it's got a lot of pull towards the electron so that it can be complete octet. Whereas metals, they don't really need extra electrons. They want to get rid of one or two or three. So electron negativity would be much lower. So we are talking about the force that each element has, each atoms of elements have, not the extra force that's outer energy that's required for you to remove electrons. So that's a bit different from ionization energy that we were talking about. For electron negativity, as you can see in these diagrams, for each period, it goes up if you go towards right. So lithium to fluorine, it keeps increasing. But one thing I want you to notice is that noble gas is not counted because they don't need extra electrons. So noble gases like neon wouldn't have any electron negativity. So the trend goes up to the halogen, but not noble gases. If you look at the blue one on the right, you can see what happens to the group of metals there. So starting from beryllium, going down the group, magnesiums, calciums, strontium, and then so on. What's happening is that the electron negativity is going down. If you look at each period as well, the one thing that I want you to notice is that things happen periodically. So the trend happens periodically. Again, for electron negativity, it starts very low because it's metals what you're talking about, and it goes up until halogens of each period. And for the noble gases, you would observe no electronegativity whatsoever. So that's why you can see, hopefully, 10 here, there's no bar, and 18 here, there's no bar, and so on. Okay. So the summary of electronegativity, it goes, electronegativity increases across a period. Two reasons. The positive charges of the nucleus is increasing. The atoms have same outermost shell, so the nucleus is shielded by the same number of inner shell electrons. And that means, as you go across a period, elements get better at attracting or taking electrons from other atoms. It's excluding the noble gas. That's a note you should add. So that's for across. How about going down a group? Electronegativity decreases. I gave you an answer there. As you move down a group. So this is because as you move down a group, atoms will gain another layer of shells, which provides less attraction towards the outermost shell. What element has? That's a question that I'm asking you there. We'll talk about a bit of this later in class. The highest electronegativity in the periodic table, as well as the lowest electronegativity in the periodic table. Well, we'll look at that in here. And there are questions that you will be doing in class. Yeah, question 1, 2, 3, 4, 5 there. And we'll look at metallic and non-metallic character later in the third video. All right, thank you for watching.